Hello and welcome back to the lab. So this is really part 3 of the 415E SWR meter series of videos, but really not going to concentrate on the 415E today. Um, in order to test the 415E, I picked up a whole bunch of magical RF devices, slotted lines and carriages and terminations and pads and calibration shorts and detectors and all kinds of cool RF accessories that I may or may not have a future use for. And one of those accessories was this ingenious device, the HP Model 536A frequency meter. The RF guys I used to work with had these sitting on their desk mainly as decoration. Um, we called them the cookie jar. Sometimes you can call it the candy jar or the pickle jar even, but we always called it the cookie jar, and you can see why. So let me read to you what the owner's manual says about this cool device. The Model 536A coaxial frequency meter is used for measuring frequency in the 960 MHz to 4.2 GHz range. Good accuracy is obtained from the spiral scale. The meter contains a coaxial line coupled to a quarter wavelength coaxial resonant cavity loaded with capacitance at the bottom of the band. At resonance, power is absorbed by the cavity, producing a dip in the coaxial line power. The frequency at which this dip occurs is read directly from the dial in gigahertz. It actually says in gigahertzes. That's what it says in the manual. Gigahertzes. I don't know why it would say that, but that's what it says. Tuning is accomplished by moving a piston. A precision lead screw, which is spring loaded to prevent backlash, is used to position this piston in the cavity. Due to the design of the cavity, its electrical length is extended at lower frequencies, and there are no spurious modes. The input and output connectors are type N female. All right, so it's a tunable resonant cavity, and it absorbs, at resonance, it absorbs some of the RF energy entering it, and that dip in that loss of power can be measured at the output. So it's the way they measured frequency back in the day. I guess back in the 1950s, before they really had counters that could measure up into the gigahertz range. Um, they're not really used today, of course, but it's a fun little device to play with, and it only cost me a few dollars, and so now I own one. All right, so it's bidirectional. There's no specific input or output. It can be fed, and either terminal can be used as an input or an output. So we're going to put our RF signal in here on the right side. On the left side, we have a HP Model 420A crystal detector. So there's a crystal detector in this device. The output of that is an audio, 1 kilohertz audio tone, which feeds into the 415E. We're feeding the input to the frequency meter with our RF signal, which is at 0 dBm, modulated with a 100% modulated with an AM 1 kilohertz sine wave. Okay, so that 1 kilohertz is detected by the crystal detector and will be indicated on the 415E power meter, SWR meter. Okay, so we're going to check a couple different frequencies, and we'll make a reading off the frequency meter, and we'll see if this thing can actually measure frequency. So let's turn the power on. Now I set my RF generator to 940 megahertz, which is the lowest frequency that this instrument can measure. Okay. Now we're going to set a reference up here for 0 dBm. And we're going to tune until we see a dip. There's a dip. You look at the meter. Let's shift the meter to expand mode and tune again for a dip. So now we're looking at a dip. Oh, let's set our 0 over here. Okay. Okay, so at resonance, The frequency meter absorbs some of the RF energy, and we get a dip at the output. It's not very much of a dip. At this bottom end, it looks like it only dipped about 0.3 dB, 0.2 dB actually. It dipped about 0.2 dB. And so now we can read the frequency directly off the meter. You read in between the two red parallel lines along this vertical needle indicator right here. The frequency is 942 megahertz. 942 megahertz. And we're putting in 940 megahertz. So it's off by 2 megahertz at this bottom end. But it does work. All right, let's try it at a higher frequency. Let's try 1 gigahertz. So we change the frequency to 1 gigahertz. You see our RF is gone back up to full power, 0 dB. And we'll tune until we see a dip again. There's a dip. I don't know how well you can see that. How it absorbs the RF energy. And when you're right at resonance, you read the frequency off the meter in between the two red parallel lines. And it's 1.001. It's off by 1 megahertz, 1%. No, 1/10 of 1% at the 1 gigahertz reading. It's off by 1/10 of 1%. 1.001. That's exactly what it reads. Okay, let's try 2 gigahertz. Let me pause it, and we'll come back when I'm close to 2 gigahertz. Okay, I had to crank the knob on the cookie jar pretty far up so we can get close to 2 gigahertz. We can see now our meter reads maximum at 0 dB. As we turn the knob and it hits resonance, oh, see, there's a nice big dip there. See, at the 2 gigahertz range, the dip is much deeper. It absorbs the frequency a lot better, but we can read the frequency directly off the scale. At 2 gigahertz, it's slightly low. It reads, what is that? 1.9. 1.990. 1.990. It's low by 1 megahertz at the 2 gigahertz frequency range. 1.990. Okay, my generator goes up to 2.1 gigahertz, so I'm going to have to switch generators to go higher than this. So we'll switch over to the 8672A synthesizer and repeat the experiment for 3 gigahertz and 4.2 gigahertz as we go up in frequency. Let's do that now. All right, let's switch to the other synthesizer, and now we're going to check the 3 gigahertz range. And I dialed this one up close to 3 gigahertz, 2.90, 2.92, 2.94, 2.96, 2.98, and we're going to tune for a dip. You can see there's our dip. Let's switch to expand so that we can see the dip more precisely. And you can see that the dip is quite pronounced here. At 3 gigahertz, our dip is about 0.8 dB. And if we read the frequency at 3 gigahertz, seems to be slightly off again, 2.998. 2.998 gigahertz. Slightly off, but very close, 2.998. That's pretty good for just a mechanical device. All right, I'm going to check 4.2 gigahertz, which is as high as this instrument can measure. So let's do that. Okay, so we've changed the frequency to 4.2 gigahertz. And now we're at 4.15, 16, 17, 18, 19. And there's our dip. Let's switch to expand mode again over here. And the dip at 4.2 gigahertz is around 1.2 dB. It's a pretty substantial dip. We're absorbing 1.2 decibels of that RF energy with the tune resonant circuit here. And then we read the frequency off the meter. And would you look at that? 4.200 gigahertz. It's spot on at 4.2 gigahertz. It's spot on. It's exactly perfect at that frequency. All right, so there you have it. An ingenious little device that measures frequency through purely mechanical means. It was very inexpensive, and these are still pretty available because no one really uses them anymore, but they're a lot of fun to play with. That's the HP 536A frequency meter, the cookie jar. Thanks very much for watching. Please like and subscribe, and stay tuned for more fun with vintage Hewlett-Packard test equipment and other fun stuff. Thanks again.